Welcome back everyone. In this section we will learn about pinnacle rearrangement and oxidation of alcohols. Let's start with the pinnacle rearrangement. This kind of rearrangement reaction takes place in those alcohols where we have a hydroxyl group on two adjacent carbons as shown here. Uh, the compound shown in this reaction is 2,3-dimethyl 2,3-butane diol, and these kind of compounds are also known as glycols. And the arrangement of hydroxyl group on two adjacent carbons is also known as vicinal arrangement, or these kind of hydroxyl groups are also known as vicinal diols. This category of compounds are also known as pinnacle. That's why the reaction is known as pinnacle rearrangement. This rearrangement reaction is a type of dehydration reaction because the product of this rearrangement, or one of the product of this rearrangement, is water. So in this reaction, water is taken out of our reactant, hence this is a dehydration reaction. This acid catalyzed dehydration reaction of glycol is quite different from the dehydration of normal alcohol. This reaction has two key features. The first feature is that the glycol group, or the hydroxyl or vicinal diol group, changes to aldehyde group. So glycol group changes to aldehyde. Excuse me, ketone group. So as we can see in the product, we have a ketone group. The second key feature is that there will be a migration of a methyl group from one carbon atom to another. So for example, in this case, the methyl group highlighted in yellow will be transferred to the neighboring carbon atom. So that is another key feature, that there will be a migration of a methyl group. We account for the conversion of pinacol to pinacolone by four-step mechanism. Let's take a look at mechanism and try to understand the progress of this reaction. This reaction is catalyzed by an acid, so therefore the first step of this reaction mechanism is a transfer of proton from the acid to hydroxyl group, which converts the hydroxyl group to oxonium ion. We know that oxonium ion is much better leaving group than hydroxyl group. So in step number one of the hydroxyl group will accept a proton from the acid and the hydroxyl group of the glycol will convert into oxonium ion. So this oxonium ion is much better leaving group than hydroxyl group. This step is a rapid and reversible step, and it's not the rate determining step. In the second step, the oxonium ion will leave, resulting in the formation of a carbocation. The resulting carbocation is a tertiary carbocation, and And we know that tertiary carbocations are the most stable kind of carbocations. The third step of this mechanism involves a 1,2 methyl shift, and with this process, migration of a methyl group will take place from the adjacent carbon atom to the one where we have a positive charge, and this migration will result in formation of another carbocation, but the newly formed carbocation is more stable due to resonance. So in this case, the methyl group highlighted in yellow will migrate to the carbon atom where there is a positive charge. So this methyl group uh, will move from here to next carbon. And this move will result in formation of a new tertiary carbocation, but the newly formed tertiary carbocation is more stable due to presence of resonance. So in the final step, a cation, uh, this cation loses the proton uh, to water, resulting in formation of pinacolone product. So the final step will involve the resonance stabilized carbocation and water will remove this proton, and it will result in formation of a pinacolone in which there is a ketone group, and this product is known as pinacolone. Oxidation is defined as a process in which electrons are lost. However, in organic reactions, it is hard to visualize the transfer of electrons. Therefore, in organic reactions, oxidation is defined as a process in which either we gain oxygen atom or we lose hydrogen atom. Either one of these two processes will account for oxidation of our substance. The outcome of oxidation process of alcohols depend on whether the starting alcohol is primary, secondary, or tertiary. In case of primary alcohols, the resulting product will be an aldehyde or a carboxylic acid. Notice that in primary alcohols on alpha carbon there are two hydrogen atoms. So therefore this alcohol can lose hydrogen twice. So in other words, oxidation can be done in two steps. In first step, when one of the hydrogen is lost, uh, that's a one step of oxidation. The product will be an aldehyde, and the further oxidation of the product, that is the aldehyde, then we will obtain a carboxylic acid. So it is a two-step process. There are different reagents which can be used to perform oxidation reactions, and we will learn about those reagents in a few slides later. But in general, we denote the process of oxidation with this symbol. In this symbol, we use oxygen atom in parentheses or square brackets on top of the arrow. So this symbol denotes that an oxidation reaction is taking place. The commonly used reagent in lab for the purpose of oxidation of primary alcohols to carboxylic acid is chromic acid. Chromic acid is prepared by dissolving either chromium 6 oxide or potassium dichromate in aqueous sulfuric acid. The reaction of preparation of chromic acid from chromium 6 oxide or potassium dichromate are shown here. You will notice that in both cases the resulting product is chromic acid. The solution of chromic acid in aqueous sulfuric acid is known as Jones solution or Jones reagent. Because of the low solubility of most organic compounds in water, their oxidation by chromic acid is commonly carried out by dissolving them in acetone and then adding a stoichiometric amount of Jones reagent to complete the oxidation process. An example of such oxidation process is shown here. In this case, the primary alcohol which is being oxidized is 1-hexanol. 1-hexanol is insoluble in water, so therefore 1-hexanol is dissolved in acetone. So acetone is used as a solvent, and our oxidizing agent is chromic acid, which is a solution of chromic acid in aqueous sulfuric acid. So that's why there is some water, and the resulting oxidation will generate hexanol as first step. It should be noted that because we are using stoichiometric amount of chromic acid, the first step product is not recovered. As soon as hexanol is produced, it will be further oxidized immediately by the chromic acid to carboxylic acid. So although this reaction is a two-step process, but we cannot isolate the first step product. We always will obtain the final step product, which is carboxylic acid. In this case, hexanol will give us a hexanoic acid. Oxidation of secondary alcohol will result in formation of a ketone. Chromic acid can also be used as the oxidizing agent for carrying out oxidation of secondary alcohol. An example of such reaction is shown here. This reaction is carried out in presence of acetone, or acetone is used as a solvent because of low solubility of these alcohols in water. As you can see that the hydroxyl group changes to ketone group in this oxidation process. Tertiary alcohols do not undergo oxidation process. So oxidation of tertiary alcohols does not take place. So therefore, if we conduct oxidation on this alcohol, there will be no reaction. The mechanism of oxidation of alcohols with chromic acid involves two steps. Step number one is the formation of a chromate ester. For example, when we combine a secondary alcohol such as cyclohexanol, shown here, with chromic acid, it will result in formation of a alkyl chromate and a loss of water molecule. In this first step, there is no change in oxidation state of either chromium or the carbon atom. So no oxidation has taken place yet. The second step involves the reaction of the chromate ester with a base, water in this example, and it will result in the formation of carbonyl group and reduction of chromium 6 to chromium 4. So the alkyl chromate, which was formed in first step, will react with a base such as water in this case. This base will remove this proton and chromium 6, which is in this case, will change to chromium 4. So in this step, chromium gets reduced and the oxygen or our alcohol gets oxidized. Another commonly used oxidizing agent for oxidation of alcohols is pyridinium chlorochromate, which is also written as PCC. PCC is prepared by dissolving chromium 6 oxide in aqueous HCl and then adding pyridine to the reaction mixture. This will result in formation of a solid PCC precipitates. The reaction of formation of PCC is shown here. PCC oxidations are carried out in aprotic solvents, and the most common solvent used for PCC is dichloromethane. PCC is a selective oxidizing agent, and in case of primary alcohols, it will oxidize them to aldehyde. It will not oxidize them all the way to carboxylic acid. So if we want to stop the oxidation of primary alcohols to first step, then PCC is the reagent of choice. However, if we want to oxidize primary alcohols all the way up to carboxylic acid, then we should use chromic acid. An example of PCC oxidation of primary alcohol is shown here, and as you can see, in this case, PCC oxidizes the alcohol group to carbonyl group. So it changes alcohols to aldehyde. If we use PCC to oxidize a secondary alcohol, it will still give the same product what we obtained in case of chromic acid. So the resulting oxidation product of secondary alcohol will be a ketone. So both chromic acid as well as PCC result in formation of ketones in case of secondary alcohol. Periodic acid is used for oxidation of glycols. In this oxidation process, the alcohol groups of glycol will be converted into aldehyde groups, and the bond between the carbon atoms of the glycol linkage will cleave. So for example, if we have a general glycol shown here, so the bond highlighted by yellow will cleave, and the functional groups, alcohol functional groups, will convert into aldehyde functional groups. And we will get two separate compounds with carbonyl groups. In this reaction, the periodic acid converts to iodic acid and water. The mechanism of periodic acid oxidation of glycol is divided into two steps. First step involves the formation of cyclic periodate intermediate. In this step, the oxidation state remains constant. Oxidation state of iodine is 7. So there is no change in oxidation. So hence no oxidation has taken place yet. Step number 2 involves the redistribution of electrons within the 5-member ring as shown here. And this will result in formation of two separate carbonyl groups. And periodic acid will convert into iodic acid. In this step, the oxidation state of iodine becomes 5. So therefore, there is a reduction in iodine, and that means the other substance, which was glycol, oxidation has taken place in the other substance. This mechanism is consistent with the fact that periodic acid oxidations are restricted to glycols that can form 5-membered cyclic periodate. Any glycol that cannot form such cyclic periodate is not oxidized by periodic acid. For example, this trans isomer of a bicyclic compound have hydroxide groups opposite to each other. So hence this is not able to form the 5-membered cyclic periodate intermediate. Hence this trans isomer is unreactive towards periodic acid. However, the cis isomer of same compound is able to form the 5-membered cyclic intermediate such as shown here. So it should be able to form this intermediate with the pyruvic acid. So hence this cis isomer is active and it will be oxidized with pyruvic acid, and it will form this cyclic carbonyl compound. So in conclusion, we can say that pyruvic acid will only oxidize those glycols in which hydroxy groups are cis to each other. Pyruvic acid will not oxidize trans glycols.